Good morning. This is EASWARI from Theivanai Ammal College for Women, Autonomous, Villupuram, working as assistant professor in Computer Science Department. Now I am going to discuss a topic about theory of computation. In that, I am going to discuss a subtopic of finite automata and equivalence of two finite automata. Now I am going to see what is meant by finite automata. Here's some of the abstract of finite automata. There are introduction about finite automata, what are all the features and definition, formal definition of finite automata, and what are all the types which are having covered in finite automata, equivalence of two finite automata and its examples. Next, this is the small introduction about finite automata. A finite automata or abstract machine. Abstract machine in the sense it is a theoretical model that represent a computer behavior focusing on computational capabilities rather than physical implementation. Abstract machines are used to analyze algorithm, model computation, compare computational power. And this is what abstract machine, and it is used to recognize patterns in input sequence forming basis of understanding regular languages in computer science. It consists of states, transition, input symbols. This is all processing each symbol by step. If a machine ends in accepting state, that is after processing input, it is considered as accepted, otherwise it has been rejected. So it consists of two types of finite automata. One is deterministic and another is non-deterministic, which is used to recognize a same set of regular languages. These are widely used in text processing, compilers and network protocols. And these are the features of finite automata. First is input and next output, that is this is output. This consists of states that has been represented in small q1, q2 and qn. This is the features of finite automata. And next, this is a description about features of finite automata. Input, a set of symbols or characters. A set of symbols in the sense can be represented as a alphabetic order or in numbers 0, 1, 2 and alphabetic in the sense AB. And output means either input, it is based upon the input pattern, whether machine has been accepted or rejected based upon input pattern. And this is all the states of finite automata. State relation, transition between two states, that has been represented in state relation. Output relation based upon final state. This is the formal definition of finite automata. It has been defined in tuple format, capital Q, epsilon, small q, capital F and delta symbol. Capital Q, finite set of states. Epsilon represents set of input symbols. Small q represents initial state. Capital F represents the final state. Transition function has been represented in delta symbol. Next, these are the types of finite automata. Deterministic finite automata, non-deterministic finite automata. Here what is meant by finite automata in the sense it has been represented in this format, and DFA for each input symbol, machine transition to only one state has been allowed in deterministic finite automata, that is only one transition, whereas a non-deterministic finite automata in the sense it allows a multiple transition. Here finite deterministic finite automata, it does not allows null transition, whereas non-deterministic finite automata it allows null transition. Here capital Q, set of all state, that is capital Q, epsilon, small q, capital F and a delta symbol, set of all state. Input symbols, small q initial state, that is a starting state, capital F final state, delta symbol transition function. Q multiplied by a set of input symbol which gives capital Q, that is a transition function. Next slide we will see about that in brief. Next, here the example of deterministic finite automata. Construct a DFA that accept all strings ending with A. Here epsilon input symbols I have already said. A comma B, capital Q that is representing states Q0, Q1, F is a final state. Final state has been represented in double circle, whereas starting state has been represented in single circle. This is the transition. This is the transition diagram. This is the transition table. Now going to see how it works. Here this is a state Q0, set of state, input symbol A, Q0 input symbol A, which moves to next state Q1. So here Q0, Q1 input symbol is A, which is reaches in Q1. Here Q1. Next Q0, it is going in this symbol B, moves in this state Q0. So here Q0. Next, while coming to the next state of Q1, A input symbol, Q1 A input symbol, which is comes in Q1 itself. So here represents as Q1. Next Q1 input symbol B, and it is moves to Q0. So here represents as Q0. This is how a transition function, based upon this transition diagram, transition function has been implemented. In this example, if a string ends with A means machine reaches a state Q1, then it is accepted. Next, coming to the non-deterministic finite automata. This is also similar to the finite automata, but I have already said deterministic finite automata contains only one state. Here multiple state transition will be accepted in same input, and null moves are allowed, where a machine can changes states without consuming any input. Next, that the same example, construct a non-deterministic finite automata that accepts a string ends with A. So the same inputs epsilon A comma B. Here a transition diagram, transition table. Q0, this is a initial state. This is called as final state. Double circle has been represented. Q0 input has been passed to the Q1 A input symbol. Next Q0, in Q0 state A input symbol. So this is reaches in Q0 state. So A Q0 to Q1 input symbol has been transferred to here Q1. Next, coming to the B input symbol B. So here a B input symbol, it is reaches to the Q0 state. So Q0 has been written here. So this is how a transition is following. And coming to the Q1 state, Q1, there is no transition will be done. So it allows null moves, null. So this is how non-deterministic finite automata will be functioning. Next, going to see comparison of deterministic finite automata and non-deterministic finite automata. Non-deterministic finite automata is more flexible than the deterministic finite automata, but it does not have more computational power. So this is a difference. And the next difference is every non-deterministic finite automata can be converted into equivalent deterministic finite automata, resulting DFA may have more states. I have already said DFA single transition and does not allows null moves, whereas NFA multiple transition, no null moves are allowed. So here power both NFA as well as DFA recognize the same set of regular languages. Next, equivalence of two finite state of automata. An automata is a machine that has finite number of states. So when two automata is said to be equivalent, in the sense it matches exactly same set of inputs. This is two set of automata. We'll move on the next slide. Here I have explained briefly. Final state has been represented as Fs. Final state means double circle, whereas intermediate state means one state has been moving to the next state. It has been represented as immediate state, that is non-final state. Immediate state has been represented as Is. Final state has been represented as Fs. So here, moving to here, Q1 state, Q1 state, input symbol reaches final state, so Fs. Next, Q4 input symbol C, it reaches final state, so Fs. Next, D symbol, Q1 Q2 input symbol D, it moves to immediate state, Is. Next, Q4 Q5 D symbol, immediate state. Next, Q2 Q3 D symbol, it goes to immediate state, Is. Next, Q5 Q6 C symbol, immediate state, Is. Next, Q2 to Q1 D symbol, final state, because this is the final state, so here final state. Next, Q5 to Q4, it reaches D symbol, it reaches final state, so Fs. Similarly, this has been following here. So here both automata is considered as equivalent, because it is also a final state, immediate state. Here immediate state, final state. So this is this automata has been proven as equivalent. This example is proving as a non-equivalent, that is Q1 Q2 C symbol, immediate state. So here immediate state. Q3 double symbol represent as a final state, C symbol, final state. So this is considered as invalid pair. While coming to the next, Q1 to Q1 D symbol, final state, so final state. Q3 Q4 D symbol, immediate, this is immediate state. This is also the invalid pair. So this automata has been proven that it is a invalid pair. This is not equivalent of finite automata. So that's all about the theory of computation and finite automata and equivalence of two finite automata. Thank you.